help us work through the mean or the average of discrete random variables. So again, the objective is to calculate the mean or the average of discrete random variables. The process is going to look a lot harder than what it really is at first. Something that's critical about this information is to understand all the different notations and symbols that are used to represent the same concept. So the mean or the average of discrete random variables, it can be denoted several different ways. Right? So one notation is it can just simply say mean of x, capital X. The capital X is what we looked at in the previous video, a notation for a discrete random variable. Another way that it can be denoted is using the symbol that's highlighted that looks like a letter U with a little tail on the bottom and then X. That's a Greek letter. So it can be denoted as, and most time people refer to that as UX. Right? A second way that the mean or average of discrete random variables can be recognized is by calling it the expected value. And then lastly, or expected value of x, of whatever the random variable is. And then finally, a fourth notation is it could have e parentheses x, e of x, expected value of x. So all four of those notations mean the exact same thing. So it's important that you connect all four of those together. And again, the math work, the way that we work this out is going to look complicated at first. The formula that we have that's over here in bold, capital EX, expected value of X, UX, mean of X. It has this formula, this funny symbol that we looked at briefly earlier this year, the sigma notation, and then XI times PI, where X are the individual values of the random variable X, and P is the individual probabilities. So XP or XI sub I, P sub I means that we're going to multiply. So when I come back over to this probability distribution table, so we have our probability distribution, we're going to multiply each of these individual pairs of numbers, multiply, and then we'll multiply, and then we'll multiply. And then that sigma notation means we'll come back and then add all of them together. This xi and p sub I just simply means that there is no limit of how many numbers are going to be in our probability distribution table. So whatever this last entry is, again, we multiply each of those individual pairs, and then the sigma notation means that we come back and add everything together as one summation. Okay. The first example is going to review a previous topic, and then we're going to learn about this new topic. So example number 1, Tri-State Pick 3 Lottery pays you $500 if you correctly choose a 3-digit number. Each digit must be a number between 0 through 9. So the old topic that we looked at in the previous lesson, the previous videos, how can we use this information to complete this probability distribution table? So here's our probability distribution table. Right? The only two probabilities or the only two events that we have is we can earn $0 if we lose, or we can earn $500 if we win. We want to find, first of all, what's the probability of each of those events happening? Right? So and I'm not going to make a tree diagram for this one because the tree diagram is going to be really big because we have more than just two outcomes that could occur for each digit. Instead, I'm going to look at it this way. The first digit, it tells us that each digit must be between 0 and 9. So the first digit must be somewhere between 0 and 9. So there's only one way that we can get that digit right, and that's to pick the correct digit. So the probability of us getting the first digit right is the fraction or the probability 1 out of 10. There's one number that's right, and there's a total of 10 digits, 0 through 9. The probability that we get the second digit right, again, the second digit must be 0 through 9 because those digits can repeat. So each digit or each event is independent of all the other ones. So the probability of getting the second digit right is once again 1 out of 10. And then lastly, the probability of getting the third digit right. The third digit must be 0 through 9. So the probability of getting the third digit right is 1 out of 10. So instead of making a tree diagram, I'm making a probability of each individual digit or each individual event. Now, what's the probability that we get all three of these right? Well, there's only one way that we can get all three of these right. So the probability that we get all three of these right means that we must get the first one right, 1 out of 10. We must get the second one right, 1 out of 10. And we must get the third one right, 1 out of 10. Now, the way that we put all this together is by multiplying those probabilities together. So the probability that we get all three of these right, when I multiply this together, is 1 out of 1,000. So what that means is the probability that we win this lottery, the probability that we win this lottery is 1 out of 1,000. Well, if we win the lottery, then we get paid $500. So winning the lottery, we get paid $500. That probability is 1 out of 1,000. Now, if we lose the lottery, we get paid 0. So the $0 matches up with losing the lottery. So we need to do a little thinking here to figure out, well, what's the probability that we lose? Well, the probability that we win is 1 out of 1,000. So there's only one way that we can win out of 1,000 possible outcomes. Well, if it's not that one way, then we lose. So the probability that we lose this lottery is 999 out of 1,000. I'm going to pause for a moment, let that kind of sink in. So the only way that we can win this lottery is to get all three digits exactly right in the right order. And the only way that can happen is one way out of 1,000 possible outcomes. So if only one way allows us to win, that means all the other 999 ways means that we lose. So that's where this probability of losing comes from. Right? The math behind that is this is the math process also. The whole number 1 minus 1 out of 1 over 1,000. So that's a mathematical way of working through that as well. So the probability that we lose is 999 out of 1,000. So that is reviewing something that we covered in a previous lesson where we talked about how to make a probability table. Right? That is not new material. That does not apply yet to the vocabulary words that we had at the top. I'm just trying to write this a little bit neater. 999 over 1,000. That's the probability that we lose. So we've completed the distribution table. Check. Now we want to calculate the mean payoff for each dollar played. So that's that UX symbol, mean payoff, and that UX symbol. So now we're going to use this new formula that we discussed at the top. So again, the math behind this new formula, without it looking so complicated, is we're going to multiply each of these individual pairs together. So we're going to multiply $0 times 999 over 1,000. And then we're going to add to that when we multiply the win column, $500 times 1 over 1,000. So this purple work is the arithmetic to find the mean payoff, right? Or the mean value, expected value, all of those vocabulary words that we discussed at the top. And then after we do this arithmetic, we're going to discuss what does it really mean in the context of this problem. So if I carefully work this out, 0 times anything is 0, plus 500 times 1 over 1,000 is 0.5. So our mean payoff expected value is 0.5. So what does that really mean in the context of this problem? Well, it's asking us, calculate the mean payoff for each dollar played. So that 0.5 in the context of this problem means that for each dollar played, every time you play $1, every time you spend $1 to play this lottery, you should expect to get back only 50 cents. 0.5 is 50 cents. So every dollar you play, you spend $1, you should expect to get back 50 cents. So if you're wondering that doesn't make sense, well, that simply means that in the long run, you should expect to lose half of the money that you spend playing this lottery. So for each dollar that you play, you should expect to get back only 50 cents. And that's the way most lottery systems work. They're set up in a way that in the long run, you're not going to win. It's set up in a way that the lottery company, the lottery organization, makes a lot of profit. The second example is going to be a little time consuming just because it's a long table. So Benford's law states that the first digit in legitimate records follow this distribution. So don't worry about what Benford's law is truly about or what does it mean by legitimate records. So using this probability distribution table, let's calculate the mean of x, or that ux. So again, the process is we're going to multiply each of these individual pairs. So all of these individual pairs, we're going to multiply all of these together, and then we'll add that up. So I'm going to writing it down and typing it in is more time consuming than really understanding what math to do. Right? But it's important that we know mean of x, or we know this ux, or we know expected value of x, or e parentheses x. We must know that all of those notations mean this math work. So 1 times 0.301, and then we add to that 2 times 0.176, and then we add to that 3 times 0.125. And I'm going to go across that table, multiplying each of those pairs together. 4 times 0.097. And as I multiply each of those pairs together, we then add all of those results to finish it out. Now, obviously, I'm about to run out of room here. So 6 times 0.067. And then continuing with plus 7 times 0.058, and then 8 times 0.051, and then finishing up with 9 times 0.046. So it's a lot of arithmetic. It's a lot of numbers. Carefully type that into Desmos or carefully type that into a calculator, whatever you have available. I'm going to trust that you can carefully type that in. And if we carefully type this in, we should get a final result of 3.41. I'm sorry, 3.441. So again, I'm going to trust for you to type that into the calculator. If you type that in and you don't get that result, then double check what you typed in, because it's very easy to make a slight mistake with typing this in. But I've multiplied each of those pairs of numbers and then add them all together. So the mean of x, the expected value of x, is 3.441. So we have the probability of each number. So the probability that the first digit is 1 is 0.301. But when we crunch all this together, the expected first digit is 3.441. So about 3 or 4, somewhere in that range would be the expected first digit. That's what this 3.441 represents. Right. A couple more examples to continue practicing this arithmetic. Right. Next example, Gain Communications sells aircraft communications units to both the military and the civilian markets. Next year's sales depend on market conditions that cannot be predicted exactly. So Gain follows the modern practice of using the probability estimates of sales. So business, this probability distribution table and this mean expected value concept carries out into the business world. So it's asking us to calculate the mean of X. Again, mean of X, or it could say expected value. And we have that UX symbol. I want you to continue to hear it and see it so you learn that all of these things mean the same thing. So my arithmetic, this one's going to be much faster. We're going to multiply each of these pairs together and then add them all up. So 1,000 times 0.1 plus 3,000 times 0.3 plus 5,000 times 0.4, and then lastly plus 10,000 times 0.2. So the probability distribution table, this gives us the probability of each of these individual events occurring. If we multiply those pairs together and then add all of that up, it gives us the expected value for that whole problem. And if we carefully multiply all this out and add it together, we should end up with the number 5,000. So what that means in the context of this problem is that Gain Communications should expect to sell about 5,000 of their communication units in the military division. If they sell less than 5,000, then they did not meet expectation. If they sell more than 5,000, then they exceed expectation. So that's where this falls into the business world. This gives companies an expectation of what they should be able to do based off of past experiences or based off of estimates of sales. So it's a practice that is used in the business industry. So this is information focusing on the military division. Right? The next example, since they also sell to the civilian market, right, still Gain Communications, but this time we want to calculate what's their expectation selling to the civilian market, the civilian division. All right, so notice how our numbers have changed slightly, but we still do the same arithmetic. We still multiply each of these pairs together and then add those values. So it's 1,000 times 0.2, 3,000 times 0.35, 5,000 times 0.25, and then lastly 10,000 times 0.2. Something to make sure I emphasize here again, I didn't mention it previously, so I'll make sure I bring it up now. The probability, each of these probabilities should still total the whole number 1, which they do. So in a probability table, all of the probabilities across the bottom should total to be the whole number 1. If I multiply each of these groups together and then add them up, this time we should get an expected value of 4,500. I trust you to be able to do that arithmetic. If you're not getting 4,500, then double check the arithmetic that you did in your calculator. So what does that mean in the context of this problem? That Gain Communications should, for next year, should expect to sell about 4,500 units in the civilian market. Anything less than that, they're not meeting expectations. Anything more than that, then they are exceeding expectations. So this expected value or this mean of X concept gives companies an opportunity to create a legitimate expectation for their sales market and sales division. One more example, maybe hit home a little bit closer with some of you, the grades, students' grades. So suppose a student creates the following probability of distribution table for their final grade. Right. A grade in the 90s, 0.05 probability, 80s, 0.30, 70s, 0.25, and so on. Calculate the mean of X, or calculate their expected value. So this gives them a legitimate expectation based off of this probability distribution table. What is a legitimate expectation for a grade for this student to make? So again, I'm going to use the same arithmetic. I'm going to multiply each of these pairs. If I multiply each of these pairs and then add those values, that should give us the expected value for this student, the legitimate expectation for what this student should do or grade they should make. Again, it's going to take a little bit of space going across the screen. A grade of 90s. Now, often students will ask, well, 90s, what number do I use? 90, 91, 92, 93? Well, anything in the 90s will give us an A. So I like to always use the minimum value, the smallest value that would get us an A. So I'm just going to stick strictly with the 90. It allows my calculations to be a little bit easier, more fluid to work through. So 90 times 0.05, and then 80 times 0.30, 70 times 0.25, 60 times 0.15, 50 times 0.10, 40 times 0.05. I'm going to continue the last two right below it, plus 30 times 0.05, and then finally 20 times 0.05. So again, I've carefully set up multiplying each of the pairs together, and then I would type that into the calculator all at one time using Desmos. It's a very handy tool, calculator tool. If I carefully type all of that in, the mean of X, also known as the expected value of X, or in this case, the expected grade, the expected value or the expected grade for this student works out to be a 64.5. So that is without any kind of quote unquote intervention. So if that's the expected grade a student has and they want to do better than that, well, then obviously the student needs to make sure they do their daily work and they prepare for quizzes and tests so that they can exceed that expectation. So I hope this video helps you with working through the arithmetic for expected value, um, E parentheses X, mean of X, that U of X notation. They all mean the same thing, and it's this arithmetic that you still see on the screen.